Let me introduce David. David's a student at the University of Melbourne and did an excellent summer project on AlphaFold, some of which he'll now present. So thanks a lot, David.
Okay, thank you, Daniel. So I think the easiest way to describe AlphaFold is a attention-based neural network that solves the protein folding problem. So let me just quickly write that up for you, and then I will be abbreviating AlphaFold as AF. Attention-based neural network. I'll just give a brief description of the protein folding problem as well. So proteins are the essential building blocks of any living organism, and their function is highly dependent on the shape into which it folds. A protein itself has a primary structure, which is just a one-dimensional sequence of proteins. So let's say just list some proteins, etc. And its tertiary structure is what unlocks its biological function, and it will just be some kind of 3D shape that will enable it to perform the functions it needs to. And so basically, I think this is, in one respect, a groundbreaking result that AlphaFold can achieve, in that it is able to compute a natural biological process. But on the other hand, I also think that there is a broader significance to AlphaFold's success, in that it is a marker of how machine learning and artificial intelligence has reached, how machine learning has reached a degree of artificial intelligence, in that it can reason and not just use high like a lot of computing power to brute force a solution. And so I like to think of AlphaFold as somewhat of a stepping stone in the AI development journey, which bridges previous machine learning successes in sort of narrower fields such as chess or Go, and really sort of unlocking the potential for AI to solve more real-world problems. So today, I will be presenting four general purpose features, which I believe is the catalyst for AlphaFold to reason in the way that I just described. I'll just write them up for you, and then we will go to the next slide and illustrate. So the four general purpose features are communication, gating, the incorporation of triangles, and lastly, adaptive computation time. There we go. Okay, so the reason why I call them general purpose features is because they are not bounded to AlphaFold in the way that other engineering features of AlphaFold may be. Actually, 3 out of these 4 features weren't actually introduced in AlphaFold, but were introduced in other neural networks. And I believe the team at DeepMind sort of picked them up and realized that they could be applied to AlphaFold, and through that process enabled greater performance by AlphaFold. So I will just call it. So even though I don't think there's a technical definition, I like to think of them as general purpose for that reason. Perfect. So I will come back to the pseudocode in a bit. So we'll just leave it off here for now.
I think probably it's fair to say the triangular attention is kind of original to AlphaFold. I mean, you could say it was in our in our ICLR paper, but that was read by a very small number of people. So
Yes, I was, yeah. So actually, triangles was the one that I was thinking was original to AlphaFold, and the three others, I picked up, or I
right, yeah,
saw
okay.
a strong resemblance in sort of some other papers. But yeah,
Yeah, I was a bit confused by the grouping you gave with general purpose features, but right, so 1, 2, and
yeah,
4 maybe
yes,
sort of imports. Yeah. Mhm.
yeah, yeah. Sorry, I should have been a bit more clearer. Okay, so so now coming over to the network overview, which is the top, I guess, picture over here. So essentially, AlphaFold is an end-to-end neural network, meaning that you provide a 1D contiguous input of the protein, and it will emit, and then in the end, it will output a 3D structure without without the person inputting having to do any additional work. Once the input is processed, will AlphaFold will query a lot of protein databases and construct two different representations of this protein. The top one, called the MSA, which stands for multiple sequence alignment. Sorry, the pen is acting up. Not sure why. Sorry, give me 1 second. There we go. So the first row in the multiple sequence alignment is the protein in question that we are trying to understand its 3D structure, and all the rows below that are protein sequences that have some sort of similar evolutionary history from other living organisms. So they had like the little fish there and chickens. But yeah, so essentially the idea behind having this MSA representation is that there is a lot of insight into how a protein can be folded through its evolutionary history. This is sort of the dominant, I guess, approach to modeling protein folding in the past couple of years before AlphaFold. Okay, and then the other representation of the protein is the pair representation, which takes
Sorry, could I
the
just ask a
residues.
question about that?
Sure.
So the only information in this database are the sequences themselves, not anything about the shapes, right? So what is the hypothesis that allows you to infer something about shape from the existence of these homologous sequences in other organisms? It's that the variation within, say, mammals or whatever should conserve the parts of the protein that actually matter or that are close together, or
Yes. So in that respect, so even though a lot of these proteins may have slightly different sequences, but and in different organisms, they to perform the same function, they still need to retain some sort of similarity in shape. And yes, so that's sort of where the, I guess, information is meant to be learnt, in that even though the sequences are different, the overall shapes end up being rather similar through in these other organisms. And so that is why the MSA has been considered very important in this in solving the protein folding problem.
thanks.
Thank you. Great. And then so yeah, the pair representation takes each of the residues. So you can just think of each residue as the part of the amino acid that has the most influence on the overall 3D shape of the protein. So each amino acid has one residue, and basically the pair representation creates a histogram creates a symmetric histogram with all the residues. So this, sorry, the pen again. I can't write for some reason.
What's the problem with the pen? It doesn't let you write.
Yeah.
Strange.
Yeah. I think it might be something to do with my my actual pen, because I can write with my finger but not my pen.
Is it low on battery, perhaps?
Yes, I was thinking that, but yes. So these two sort of these two sequences would be identical, and so the pair representation is meant to be considered as, or the pair representation provides more of a geometric and physical input into how the final protein will end up being folded. So these two are the main inputs. So the MSA and the pair representation, they're the main inputs into the evoformer, which is the part of the network that is mostly concerned with attention and creating the overall distance, and generating values for the distances between residues. There are sort of two, I guess, different towers in the evoformer that, although they process the MSA and the pair representations separately, there are two different channels of communication that allow them to refine hypotheses and generate hypotheses in the first place, and then refine them or discard them. So the MSA will pass genetic information to the pair representation through a pair bias. Sorry, let me restart. So the MSA will pass genetic information to the pair representation through an outer product mean, and the pair representation will pass information back to the MSA through a pair bias. Essentially, what is happening in this stage is the MSA will contain the genetic data, and they will say, okay, so in fishes, chickens, and cows, we found that proteins that are rather similar and perform similar functions have this sort of shape. So that's what it will communicate to the pair representation, and the pair representation will take this hypothesis and test it using the triangular attention that we'll get to next. But essentially, it will either conclude that this hypothesis can be refined further or can be discarded, and maybe when it refines this data, it will find that, okay, so if this protein has a particular shape in which residues A and B are very close, then this means that residues C and D must also be close. And this information gets passed back to the MSA, and the MSA, it is now the MSA's job to perform a similar role in determining whether or not this hypothesis has any merit and whether they should keep refining it. So this sort of continuous communication process is a relatively, even though it seems, even though it is very common in AlphaFold, this type of communication hasn't really happened in a lot of other protein folding algorithms. Mainly, this communication only happens once at the end of training, whereas in AlphaFold, this communication happens 96 times per cycle, which is why I think, which definitely contributes to the accuracy of AlphaFold. So that is.
Check so in the pair representation, these R indices range over all the sequences that appear in all the animals or all the rows in the MSA database, or there's some sort of clustering going on with these sequences, right, somewhere?
Yes. Yep. So the clustering happens when the MSA gets embedded from the database. I was going to talk about that in the next general purpose feature. But the pair representation or the dimensions of the pair representation matrix is just the amount of residues by the amount of residues. And when it first gets embedded, it doesn't contain any evolutionary information outside of outside of the information that can be embedded within it at the beginning of training.
Mm-hmm.
But yes, so coming back to this idea of communication, let's move to the board below. And so this is the pseudocode for the MSA row attention refinement and with the pair bias. So this pair bias, which gets introduced in line 3. So this line here, and which enters into attention in line 5. That is how the geometric pair representation is transmitting information through to the MSA. So I'm not going to go too much into the details of the other pseudocode because that is that is, I guess, what isn't the general purpose feature here. But this addition of the pair bias after the dot product of the query and key vector when performing attention, I believe has a logical sort of interpretation in Boolean logic. So I think it is more insightful to consider why the authors did not choose to for the bias to enter the MSA through multiplication, as opposed to trying to interpret why it's addition. Because in Boolean logic, addition being interpreted as the logical expression or is a lot more vague than interpreting multiplication as conjunction. So I think the reason why there is no sort of sense of conjunction here is that the DeepMind did not wish for attention to focus on what the MSA and pair representations had in common, because, as I said before, the main process of this communication is to try and generate new hypotheses. Then this additive bias should try and provide new, even though some of them might not necessarily be good suggestions. They should try and suggest new ones for the MSA and the pair representation to refine to test through the rest of the block. So this is sort of why I think in line 5 the pair bias term is added as opposed to taking any other form of entering attention. And this takes me across to the next piece of pseudocode. So the next piece of pseudocode we're going to consider is the top one, which defines the outer product mean algorithm. So this is the algorithm by which the MSA transmits genetic information through to the pair representation. There will be some other points that I raise about this code later, but essentially what I believe the outer product in line 3 is doing, it is creating some kind of binding between the two different residues. I'll illustrate what I mean. So we have the MSA here. Sorry, I'm drawing with my finger, so my handwriting is not that great. But essentially, this is column I, and then over here we have column J. Each ASI and BSJ, which are the left-hand side and right-hand side of the outer or tensor product in line 3, is one entry in each. Sorry. Oh, this is it's a bit annoying not being able to draw with the pen. Sorry. But yes, so one grid in that column would be A and B, and the reason why they're vectors is because they are like there's different channels behind the MSA, which I'm not going to talk too much into, but essentially this tensor product binds the information contained within both of these vectors, or I guess single values if you just want to consider it as a matrix. It binds the information together in a manner that is almost similar to tensor product representations in NLP. And I think the reason for this is because when you're transmitting this information about like purely concerning these two residues, you're not looking. Basically, you want to transmit this information so that the pair representation is able to gain some idea of the distance relating the two, and this process of binding is I guess the way to convey the most information, because you are essentially producing the product of each possible combination of multiplication between all of the values in the MSA. And so you are passing the entirety of genetic information in this one step over to the pair representation. And essentially after this, so each time you do the A tensor product B, you will do this for each pair in the column, and then you'll take the mean of all of these different tensors across the column. So let's say you have A1 and B1 gives O1, and then A2 tensor B2 gives O2. And then you'll average all of these, or you'll do an element-wise average of all of the O tensors, and then in the end, you'll have through another linear transformation, you'll end up with just a single entry into the pair representation. But also the reason why I think they take the mean here is that the mean is essentially just summing and then dividing by a constant. So there is, I think, an element of layer normalization here by dividing, and then taking the sum doesn't impact the level of learning because you perform an affine transformation to the summed matrix afterwards. So basically these two algorithms, the one on the previous board and this outer product mean, combine to form communication, which is the first general purpose feature. Next, I will talk about gating. So gating is a concept that was first introduced in LSTMs, which stands for long short-term memory, and is meant to remedy exploding and vanishing gradients in recurrent neural networks. A gate's interpretation is essentially regulating memory and which pieces of information to remember and which pieces of information to forget. This can be achieved through sigmoid functions on affine or linear transformations of your data. So if we look at this pseudocode defined as triangle multiplication outgoing, we can see that there are sort of two types of gates in this algorithm. So we have one gate here and one gate here. Oh, and just to briefly talk about the sigmoid function. So essentially, the sigmoid function squeezes values between squeezes a value between 0 and 1. And the interpretation of this is that if you have, when you do this pointwise product, if a value in the gate is close to 0, that means forget the corresponding entry of the data, and then 1 means to remember. So that is the interpretation.
Maybe it's just worth saying, since this circle with the dot is not really standard mathematical notation, that this means take two vectors and multiply them entry-wise, as you just said.
Yeah, sorry. Yeah, so the circle with the dot is element-wise product. Great. So this gate, and just there's another comment as well. So because gates were introduced in LSTMs, and as far as I had looked, if they weren't used very regularly elsewhere, I've chosen to, I will continue to speak sort of using their language, the language of LSTMs, but I'll try and qualify what I say. So in this algorithm, there is both a input gate and an output gate. So I'll explain what I mean. So this first gate here is the input gate, which essentially regulates what information actually carries through from the previous representation of the data. So I think the reason why they do this is because in sort of the biochemistry of protein folding, there are certain residues that can form stronger bonds, and hence they are more important in sort of determining the protein structure. And so in this sense, they are trying to maybe not use the gate to remember or forget, but try and pass along which pieces of information are more important to model in this specific step. And so maybe the idea of forgetting and remembering isn't as important, but it is to regulate the information flow into this layer of refinement. The gate which is constructed in line 3 and used in line 4, this is the output gate. And this is the gate that regulates which structural hypotheses are worth passing on to the next layer for refinement and which ones should be forgotten. So in this sense, a much more, I guess, regular interpretation of what a gate is, or at least what corresponds to in LSTMs. So this is an example of an algorithm that uses both input and output gates. But I will come back to another board to illustrate a algorithm with only an output gate and explain why. So in this algorithm, in the row attention with pair bias algorithm again, we are constructing the output gate here in line 4 and utilizing it in line 6. But crucially here, there is no input gate. There is only an output gate. And this comes back to the idea of clustering that Dan raised before when I was talking about the embedding of the MSA. So because of the high sort of data costs associated with a lot of these processes in the algorithm, it is desirable for DeepMind to reduce the number of sequences they use in the MSA while they try not to sacrifice any information. So essentially, what clustering does is It groups all the similar sequences. It groups all sequences by similarity into different clusters. They have a technical process for this, which is in the supplementary material, but I won't go into. Once they have all these clusters, representatives are chosen from each cluster, and then this is what actually forms the true MSA. Again, through the embedding process, and this is described in the supplementary materials as well, they are able to embed each of these representatives from each cluster with information pertaining to their cluster. So not too much information is lost. However, it does make computation a lot quicker and easier. And this comes back to my point of not using an input gate, which is that they don't want to sacrifice any, or like they've already sacrificed a little bit of information in this clustering process to allow for easier computation. And so they don't want to sacrifice any additional information at this stage, which is why there is only an output gate and no input gate in this algorithm. The output gate, in my opinion, here plays a similar role as in the previous slide, which is just that it would regulate which hypotheses to remember or forget before passing to the next layer to be refined. Okay, I will now move to the big diagram. So before I start talking about the diagram, I will introduce the third general purpose feature, which is adaptive computation time. So this was introduced again in recurrent neural networks, and basically it allows the network to dynamically learn how many cycles or repetitions to sort of think about or compute its input before outputting the next state. So basically the reason for this is that research shows deeper networks definitely perform better, but definitely also take up more computation memory. And so there is some sort of trade-off there. And ACT allows adaptive computation time, ACT, allows the network to learn how deep it should extend itself. Despite the fact that AlphaFold has a fixed amount of repetitions, that is like an engineering feature designed by DeepMind, I believe that there is evidence that ACT is being achieved, and I believe it is done through two different mechanisms. So one is called invariant point attention, which I actually forgot to outline before, but essentially it is not in the Evo former, but it is in the next trunk of the network, which maps the histogram and which maps the histogram into an actual 3D into the 3D coordinates of the protein. And invariant point attention simply means that invariant point attention invariant point attention it's when the structure module is mapping the coordinates into 3D space, this attention instructs AlphaFold to disregard any global rotations or translations, as they have no effect on the overall 3D shape physically and geometrically. And invariant point attention is the way DeepMind tells AlphaFold to do this. So the fact that IPA can be introduced into the structure module means that there are a lot less hypotheses they need to test, because they understand that rotation and translation doesn't affect the overall 3D shape of the protein. The second point, recycling, is essentially using the previous cycle's output as the new cycle's input. So what I mean by that is AlphaFold is trained sort of 3 consecutive times and each time the output is recycled as the input for the next training cycle. And because there are sort of like an infinite set of proteins that can be sort of created, and the longer the protein chain, although not always, but the longer the protein chain, generally it is harder to model the 3D shape of that protein, which is why there are sort of differences in protein databases that specialize in, I guess, the difficulty of how hard it is to understand the 3D shape of a protein. And so recycling, in accompaniment to recycling, AlphaFold has a associated sort of feature with every protein that determines a accuracy estimate for a protein it has produced. And so this is fed along with the previous output through to the next input. And so essentially, if a protein has a low estimate of accuracy, then this allows the network more time and more computation to work on this specific protein. I'll just demonstrate the evidence here. It's in picture B, so the one below at the bottom. So both the blue and orange lines represent protein data banks that have easier to fold proteins. And so the accuracy, so the y-axis is global distance as a measure of error, essentially. As a measure of accuracy. And as you can see, the proteins from the, I guess, easier database to fold reach high accuracy very quickly, essentially within the first cycle, which is 48 blocks. However, the green line, which represents harder to fold proteins, take essentially almost the entire 4 cycles to achieve not even as high an accuracy as what was achieved halfway through the first cycle for the other proteins. So without recycling, so if let's say they stopped at 48 blocks, AlphaFold's accuracy regarding a lot of harder proteins would just simply fail because they essentially do not allow for adaptive computation time to work longer and harder on a harder protein. And then talking about figure 6a. So 6a is the ablation, not 6a, just A. It represents the ablation studies done by DeepMind on AlphaFold. And we are just interested in this line, and this line. Oh, and this line. All the other lines are still interesting, but these ones are the ones we are focusing on for ACT. And as you can see, excluding IPA and excluding recycling, do not by themselves do not create that much of a dent in accuracy. Again, the x-axis is a measure of accuracy, whereas excluding both of them has a very significant impact on what AlphaFold is able to predict. So there is sort of some kind of non-linearity here, which I believe hints at the fact that these two features have an interactive role. And I think the interpretation of this is that omitting both of these features significantly increases the number of incorrect or wrong models that AlphaFold has to compute. The lack of recycling means that there's just less blocks to compute, whereas removing IPA means that it just increases. If the protein were to be rotated, it still has the same 3D shape. However, AlphaFold would treat it as a different hypothesis and we'll have to compute that separately.
Yeah, that's an interesting observation. It is kind of weird that turning off IPA has this fairly small drop, and then. But yeah, I guess I agree with your interpretation there. It seems like both are a form of focusing your computation on something that matters.
Yeah, I think that is definitely like a neat way to look at it. It just focuses all the computation power on either refining a model that is sort of like in figure B, that sort of continuously improves the accuracy throughout the recycling, throughout the different cycles, and reducing the number of wrong hypotheses that the model has to compute. And that is the third general purpose feature, adaptive computation time. Now moving over to the last board for triangles. Okay, so I think, as Dan pointed out, the triangular attention is, I guess, the most innovative feature of this AlphaFold network. And it begins by sort of thinking about the protein folding problem as sort of like a graph problem. So in here, each sort of I, J, and K, the circles represent a residue. And the line, so the arrows between these residues represent the distance. And it is these distances that make up the pair representation. So essentially what's happened here is that the pair representation has been transformed into a graph problem. And these are the diagrams for the two different types of attention that are performed in the form of triangles. And there's two different types. I don't want to go too much into the difference between the two because I think there is sort of like a symmetry to understanding why, or if you understand why you perform the triangular attention around the starting node, it will be easy to translate that into why you also perform it around the ending node. So I would just focus on the left-hand sort of diagram for this talk. So in this diagram with triangular self-attention, it is the red arrow, so the distance between residues I and J, that is being updated. And so accordingly, because it's performing attention, this is the value that produces the query vector for attention. And then this K residue here. So I've just drawn one single K just to, I guess, make it easier to illustrate. But essentially, you'll be performing this process with every other residue that is not I or J, and then doing a affine transformation on that. So even though there is just one K here, keep in mind that you'll be essentially modeling the relations of this triangle for every residue triplet containing I, J, and some other residue. Okay, so through this sort of triangular graph, what happens is that the key and value vectors used in attention are produced from the green line, which I've also labeled, and then the bias term is produced on the distance from J to K. Personally, I think that the reason why one big reason why they've decided to use this triangular attention is because even though in the 1D input it is a contiguous sort of chain, once it starts curling up, and because of the chemical interactions, every residue will have an impact on every other residue, even if it's extremely small. But often it is these sort of small chemical interactions that can cause the protein to fold in a completely different way. And so I think that this sort of triangular attention will allow the algorithm to focus on modeling these sort of really nuanced and I guess partial attractions within the biochemistry of the problem.
But what you just said would be also consistent as a justification of just pairwise attention rather than triangular attention, right? Every residue needs to attend to every other residue, but that doesn't really give an explanation for why you need somehow a term that involves triples of residues.
Okay. Yeah. Yeah, I get what you mean. Okay,
I don't know. I don't know the answer either. Maybe I'll spitball something and you tell me it makes sense or not. I mean, if all these residues are folded up in a complicated 3D shape, then you can't really understand the forces involved in terms of pairs, because you might have two residues effectively holding a third in place together, right? Because they're, like, for example, on either side of it and exerting forces that partly cancel out. So that there are a lot of interactions here that literally are three-way interactions, and you can't ignore them. I suppose in principle there might be four-way interactions and higher, but apparently they're not necessary to get a good level of performance. I don't know. Is that? I don't actually remember exactly what the justification DeepMind gives for triangular attention is.
Mm-hmm. Yeah. I think, yeah. So I guess I really like that explanation, and I guess in the same vein, it just allows AlphaFold to model more complex, relations between these three entities at one time. And yeah, I think, as Dan said, it is like, I think generalizing to 4 or like 5 residues, dealing with 4 or 5 residues with attention at the same time will improve accuracy, but with just highly diminishing returns in terms of computation trade-off with increased accuracy.
Yeah. If you just indulge me for a second, I think there's a diagram that helps make this point. So if you think about 3 blocks sitting on a table, interacting by contact forces, well, you can't really understand that configuration as just in terms of pairwise interactions, because, well, suppose it's the center of gravity is over the middle and such, and there's sufficient noise around that if you were to remove this block, then the top one would fall, and if you were to remove that block, the top one would fall. So neither is supporting it on its own. It's the combination of the two below that support it. That's a fairly trivial example, but you could have much more complicated situations that are essentially like that. So considering a configuration like this was sort of the motivation for the paper we wrote on logic and the two-simplicial transformer, which did something similar but not exactly the same as what DeepMind calls triangular attention. We used it on a toy problem. Of course, they used their version on a very important non-toy problem. But yeah, I think it does make sense if you're modeling collections of entities that there are many interactions, including physical ones, that cannot be understood as at least a shallow set of pairwise interactions. Given sufficient depth, you can probably model any order interaction with pairwise ones, I guess. But in practice, DeepMind seems to have shown that these kind of triply interacting entities is a good inductive bias for at least some kinds of physical problems. Sorry to interrupt.
Yeah. No, thanks, Daniel. I think that made it that was a much clearer explanation of what I was trying to give. But yes, so I think essentially the triangle attention here models the more allows for AlphaFold to model the more intricate multi-residue relationships without explicit human code, as well as yes, as well as reinforcing, I guess, the relationship Daniel was talking about, how, yeah, like it is not just pair relations that will govern a 3D shape. Okay, so that is essentially the end of all the general purpose features I wanted to talk about. And I just want to take a couple moments to, I guess, zoom out and talk about what I think AlphaFold means. So essentially, I think throughout this talk, hopefully I made it, I sort of, these general purpose features, or I didn't make it very clear at the beginning, which is my fault. But these general purpose features essentially do not contain any sort of human concepts as to why protein folding happens. It doesn't explicitly code any human knowledge, and doesn't code for AlphaFold to look for human knowledge. Instead, I think the lack of prescribed features will actually induces creativity within the network, and it allows it to learn features that the network itself deems important. In the paper that DeepMind released, they did say that even though they didn't explicitly program for hydrogen bonds, they ended up conducting some sort of studies that showed AlphaFold can effectively look for hydrogen bonds when it is trying to do this protein folding. And so, even though AlphaFold can understand human concepts, I also believe that AlphaFold's success is due to the fact that it is able to understand non-human concepts, which is where if one were to try and engineer a neural network using human knowledge or prescribing human knowledge, it cannot achieve such high accuracy. And the reason why I think, or I guess my hypothesis as to why neural networks in general, not just AlphaFold, well, at least well-designed neural networks, is able to learn these superhuman concepts, is that they're very flexible and, like I said before, creative in their, I guess, thinking or computation, in that they can switch lenses of viewing and processing information. I think this is very different to how the human brain works, because when a human learns something, they can learn it like a number of different ways, but I think that eventually you settle down on one way that you find is natural for you and easy for you, and so you always stick to that sort of way of doing something. Whereas a neural network may not be hindered by, I guess, such biases, and are able to sort of freely and flexibly switch the way it looks and processes information, and yes, achieve better outcomes than, I guess, the human brain can. And I guess linking back to the general purpose features which I discussed, so the four, such as the four, basically, or I guess gating in particular, I think is important to this, in that it helps regulate what kind of information, or how information flows throughout the network, as well as the communication, being able to use gating and communication together. So I guess gated communication between the two different streams of information, and being essentially able to use these DeepMind being able to use these general purpose features to unlock a higher level of concepts for AlphaFold to understand. I think that pretty much concludes my talk.
Thanks very much.
Thank you.
That was very useful. Any questions? Basic questions are also encouraged. Don't feel you have to ask a very specific technical question. I'll ask a basic question. Why, I mean, DeepMind has talent and money, but many people worked on the protein folding problem, and it's not like neural networks haven't been applied to this before. Do you have any sense of why it took DeepMind to crack it?
Yeah. I do think I definitely had to look at a lot of the, I guess, other entries into CASP, which was where DeepMind sort of released AlphaFold. And but yes, so I think a lot of the other neural networks were definitely, I guess, engineering-wise, just as intricate as AlphaFold, but it lacked some of these features that I talked about. So triangles, in particular, were not present in any other, I guess, entrant in CASP, as well as the fact that what I said about communication before, in that they only communicated the evolutionary and information once to the geometric representation, whereas whereas AlphaFold were able to do that a lot more times. And I do think it is these sort of general purpose features that allow AlphaFold's accuracy. But to answer your question, I just think it's more of a way of approaching the problem, and instead of trying to almost teach the machine to learn it, just help it unlock the ability to learn for itself, which I think are two sort of different things when you're trying to create a neural network.
Yeah, it's interesting that you came to that observation. So I don't want to put words in your mouth, but so you're saying something like, if you look at the other entrants, they're trying to encode more domain knowledge than it seems like DeepMind is trying to encode. Is that accurate?
Yes. I think it's just DeepMind's ability to, I guess, divorce their understanding of the protein folding problem from AlphaFold and really focusing their attention on letting AlphaFold do all of the learning. And I think some of the other entrants definitely did this, but I think part of the reason why, I guess, DeepMind succeeded first was just the manpower in some ways, I believe.
Yeah, it's clear there's a level of engineering polish to AlphaFold that is hard to achieve in an academic team, no matter how well funded.
Yeah. Yes, I think that is it, because actually, towards a couple of months before DeepMind actually released their paper, because DeepMind actually held off quite a long time before releasing the actual paper and the supplementary material after AlphaFold's success at CASP. And I was reading a couple of forums, and I think a lot of the reasons why AlphaFold felt like DeepMind rather had to release the AlphaFold papers and code is because a lot of other open source communities were approaching the accuracy of AlphaFold, and so it was sort of pressured to, it was almost pressured to sort of release the code. So I think it is almost like the funding and manpower definitely contributed.
Yeah, it's an interesting counterfactual to wonder whether this was inevitable, so that this level of performance was baked in the moment deep learning had its breakthrough in 2012 or whatever, or whether it's hard to imagine this would have never happened without DeepMind. But how many years did we skip ahead because of the existence of this research organization? I think it's not nothing.
Yes,
so
definitely.
Here's hoping for fusion and many other advances to come along these lines. Any other questions for David?
Sorry for my ignorance, but would you be able to briefly walk through the exact sense in which triangular and higher order attention generalizes pairwise attention? Maybe even just explain how attention works.
Yeah, sure. Or yeah. So basically, attention allows the neural network to focus its attention on the more important parts of the input or the data. And yet, Dan, please jump in if I say anything wrong.
I'm happy to let you speak, but Adrian's a mathematician and wants to see a formula, I think.
Okay.
So I would start writing up dot products or something, and then you'll be happier.
Yeah, sure. My pen actually still doesn't work. Sorry. Are you able to?
I'll write something over here on the right hand side.
Sorry.
Okay, so normal attention works between entities I and J by first mapping each entity. So that's entities are indexed by I. Each entity is mapped by some learned transformation, generally a linear map, to a triple of vectors, a query, a key, and a value. And then we say that entity I is attending to entity J if the dot product of the query vector for I with the key vector for J is large. So that gives a way of embedding entities into some high-dimensional space so that the network can learn to align the keys and queries so as to create message channels between entities. So that's ordinary attention. The precise mechanism, you can sort of imagine how that would work. If you keep I fixed and let J vary, you get a vector of these ranging over J's, and then you could use a softmax to turn that into a probability distribution. So the details, I think, you can see. But the essential quantity is this dot product. For higher dimensional attention, well, there's various ways to do it. So what I'm going to discuss is sort of a generic form. But if I give you a triple of entities, you might sort of maybe an oriented triple in the same way that this was an oriented pair, right? I and J are treated differently because one uses the query and one uses the key. So this number's associated to the ordered pair I, J, or the simplex, the one simplex. If I give you a two simplex, which is an ordered triple or a triangle, you could sort of imagine that. Let me divide it in two now. So this dot product of query and key at the top is kind of a means of predicting whether there's an edge in some oriented graph, right? The oriented graph being the sort of causal network, if you like, or the relationships between entities. And you could ask, well, could you predict instead of one simplices or edges connecting entities, could you instead predict the existence of higher dimensional information like triangles, three-way relationships? And that would mean, associating some vectors to I, J, and K so that some constant associated to the triple would be used to make such a prediction. DeepMind doesn't really set it up that way. That's my take on the idea, but this bias term that goes into the formula essentially contains this kind of idea. It's indexed by a triple, and its large or small affects the way in which information about entity I is updated. So at a high level, I think the ideas are the same. The implementation is guided in DeepMind's case by a very careful attention to the computational cost. But at a high level, I think it's fair to say that the idea is to learn a linear embedding of entities into a space and then use some sort of geometric algebra on that space, dot products, multiplications, etc., to figure out whether relationships between pairs, triples, quadruples, and so on of entities exist. And then if you predict them to exist, then you use them to update the various entity representations. All right. Let's thank David again. That was great, David. Thank you.
Thanks, David.
Thanks, guys. Glad you liked it.
Okay. Yeah, we'll leave it at that. I'll stop the recording, but feel free to continue asking questions. That is, if David, you're willing to stick around for a bit.
Yeah, I'm all good. Yeah.